Okay, so now let's take this one step further. Where we were using Riemann sums to find approximate areas under the curve, now we can see, and I believe I left off the A in the handout, but Theorem 5.32 just says the area under the curve can be calculated using this same formula, the antiderivative of f of x dx evaluated from A to B. Okay, so let's see an example of this. I think I have it on the next page. Find the area A of the region between the graph of y equals sine x and the x-axis from x equals 0 to x equals pi. So the first thing we want to do is rewrite this into the format, so from 0 to pi, okay, and our f of x is going to be sine of x dx. Okay, that was all the information that was given. So we're going to be looking at area under the curve between this function and the x-axis, and we're ready to go ahead and evaluate that. So by our theorem, this is simply can be rewritten in this format: sine of x dx, evaluate it there. Alright, so let's go ahead and calculate this. So what's the antiderivative of the sine of x? Good, negative cosine of x. Evaluate this from 0 to pi. Okay, so we're going to have f of b minus f of a, so that's just going to be negative cosine of pi minus negative cosine of 0. Alright, cosine of pi is going to be, hold on, maybe I can pull up a unit circle for you if you don't remember this. Okay, so we go over to cosine of pi, which is right here. The cosine's the x value. You can see right there that that's negative 1, but negative 1 times this negative 1 here is just going to be 1. Now let's go find the cosine of 0. Cosine of 0, here's 0. Cosine is the x value, so that's just going to be 1, but with the negative in front of that, it's going to be negative 1. So we have 1 minus a negative 1. It's just going to simplify to 2. Okay, this page is just a statement with some formulas for definite integrals, and maybe it would have been helpful to see this one before the last problem, but it doesn't matter. This is stuff that we've talked about antiderivatives before, but this is just to see some, and it was included in your textbook, so I just threw it in here. So, like I said, you might want to pause it and jot these down before you move on. Okay, just some practice here. This one shouldn't be too terribly bad. You should be able to work this one out. The first thing I'm going to suggest that you do is you do some algebra here. Foil this out to the side, simplify it before you take the antiderivative, and then apply the fundamental theorem of calculus and simplify this. And then I'm going to pause it and then just put the answer up and let you check your answer. Okay, our fundamental theorem of calculus stated right there. That's just our algebra we simplified, boiled it out, our antiderivative, evaluated f of b minus f of a. So this is the f of b minus the f of a right there. You can check your work. I'll leave this screen here and simplify. Here's the fraction form of your answer, and this is the decimal form. So pause it, check your work before we move to the next example. Alright, next example. This is just practice. Examples, examples, examples. So I do want to suggest right here that you factor out this sum of cubes. Right here, use your formula back in algebra. Simplify if you can, and then move on from there once you take the antiderivative. So something's going to simplify in here, so I'll let you work on that for a few minutes. Okay, before you get too far, you may want to check. This is your sum of cubes formula. We determine a to be x, that's what's cubed in this first term, B is what cube gives you 8, so that's 2. When you plug that in, plug in your A and your B into this formula, you're going to get x plus 2 times x squared minus 2x plus 4. So I replace x cubed plus 8 with that in the numerator, and then we can see here that these cancel, and now we're ready to find the antiderivative of this. So pause it and continue. Okay, when you take the antiderivative, this is what you will get. Evaluate it. F of B, capital F of B minus capital F of A right there. The left-hand side will simplify to negative 16 thirds. The right-hand side is just 0, so we get negative 16 thirds, or approximately negative 5.3 with the bar over it. Okay, I sketched this in right here, and I just want to make a side note using this property. Let me go back to the property real quick. Um, well, let's see. It's this property right here. Remember, if the A and the B, the upper and lower limits are reversed, we pull a negative out front, and then you would evaluate the opposite of that function. So let me just show you how that would work in a particular example, the one that we just worked. So I feel like it wouldn't be too difficult for you to see that. Okay, let's see. Alright, so if you can see my upper and lower limits, or if I reverse those, because negative 1 is smaller than 0, so if I reverse those, I would have to have a negative out front, which is this negative. Now we would still find the antiderivative of this in all the same ways. It's still going to be the same antiderivative. So I just copied that over there, and then of course now these two changed order. So all that means is these evaluations, these values are going to be the same, they're just going to be in a different order. So this time it'll be the 0 minus the negative 16 thirds. That's what I have here. Right here, when you add this, you're going to get positive 16 thirds in this parenthesis in the brackets. Then we have the negative out front. So you'll still get the same exact value, negative 16 thirds. This particular way is applying the property that when you change your upper limits and lower limits, we pull a negative out front. That's just for you to see that in its entirety. So let me see if I can separate this. Oops. So that on your notes you won't be confused as it's part of the problem. So that's just an extra side note.